Hi everyone. Today's topic that I'll be presenting is conversion force of concrete beam by opening. So let's go to the content. I'll briefly introduce my company first, then move on to the general features, design and analysis, conversion and an analysis of finite elements. So I'll briefly introduce myself. My name is Jinyoung Kim, CEO of JTech Engineering in South Korea and Vietnam. I'm also an adjunct professor in Hanyang University, licensed structural engineer in South Korea and Vietnam, and also a licensed APEC engineer. I'm a CEO of 5 companies of the following. First is JTech Structural Engineering, which is a company based on structural technology. Second is the JTech Seismic Technology, which is specialized in performance-based design with specialized technology in structural field. J&D Architects Office is responsible of architectural design in Korea and Vietnam. In JTech Construction Safety is construction company with facility maintenance business license. Lastly, JMP Company Limited executes same duties with the 4 companies in Seoul. So overall, this webinar is prepared for structural engineers, and the topic discusses about the issues that engineers probably thought about it at least once throughout their actual project. So let's move on to the general features. For the general features, there are a lot of cases in real projects with openings for pipes. The picture below is opening on concrete beam from the site. Figure 1 from the general note is reinforcement details on general beam opening. As you can see it from the picture, if there is an appropriate concrete opening gap, structural stability can be secured by processing it like general reinforcement and placing concrete. By appropriate concrete gap normally means under 1/3 of the concrete butt depth. In other words, if the depth of the beam is 600 millimeters, the maximum size of the opening is 200 millimeters. The appropriate distance between the openings is at least 3 times of the opening diameter. So if the size of the opening is 200 millimeters, it means that the center distance between the opening is bigger than 600 millimeters. The opening should be located on where the stress that is applied on the beam is relatively less. I'll further explain on the next page about the stress. So if an opening is located as a general opening, no further review is necessary. However, openings are not always located in the location you want. So there are times when you need to review the reinforcements separately, and this material is a method to review when the opening is not located in the location I wanted. I've briefly ran an analysis on a single span from ramen structure to determine the relatively weak beam from a gutter. I analyzed figure 1 assuming that the gravity direction load is applied. This is the bending moment diagram. As you can see, the moment is relatively small in the middle section. The second figure shows lateral force only after removing gravity direction load. In this case, an inflection point occurs in the middle section, and you can see the moment in the middle section is also relatively small. The third figure is the bending moment diagram. It shows when the force in the gravity direction and the load in the lateral direction are applied simultaneously. And in this case, changes may occur depending on the difference in the force. However, it indicates that the moment in the center or quarter point is the fewest. Therefore, it can be confirmed that the position to locate the opening of the beam is appropriate for the quarter of the beam or the central member. From now on, I would like to talk about the shear force diagram among the single-span frame analysis results. The first figure is the result of the gravity load. In this case, the minimum shear force occurs at the center by arising the inflection point there. The second figure shows the result when only lateral force is applied. You can see that the same values occur in all cross sections. The third figure is a shear force diagram when gravity load and lateral force are applied at the same time. And you can check that the inflection point occurs near the center. The location of this inflection point will depend on the relative value of gravity load and lateral force. However, we can see from the result that the shear force value is relatively low in the center, or the quarter point is similar to the moment diagram result. So, judging from these analysis results, it is most appropriate to locate an opening in the central part of the beam, since the middle section of the gutter is the point where the least load occurs. So let's move on to analysis and design. This is an example to be analyzed. Span is 9 meters ramen frame, and the load P is applied at the point 3 meters from the end. The external opening of the beam is 600 by 200 and located at the point 2 meters from center line of the end. The size of the gutter is 600 by 1000 and the size of the column is 600 by 600. Structural analysis was performed with the applied load P that has 400 kilonewton dead load and 200 kilonewton live load. Now I'll briefly introduce about the program that I have used. I used MIDAS Gen, which is a 3D general purpose analysis program to run the analysis. As you can see it here, MIDAS's program consists of several different programs. First of all, there is Gen, a 3D general purpose analysis program. And you can think of it as similar to ETAPS or SAP 2000, which is also used a lot in Vietnam right now. MIDAS ADS is specialized program for wall column structure, which is also used a lot. Next, MIDAS STS, which is a two-dimensional plate analysis program, similar to SAFE, which is mainly used in Vietnam as well. And for this case, I used MIDAS Gen and Design Plus, which is marked in red, as you can see in the screen. And Design Plus is used to design the members of the structures. So this is the start screen of MIDAS Gen. User graphic, the interface is developed in the way users can easily use, and all the menus are in English, making it convenient for engineers in any countries to use. If there's any chance later, I'll introduce how to use MIDAS for beginner and intermediate level. So I've just briefly explained MIDAS Gen, and I'll move on. Our Vietnamese engineers in my company are viewing projects using MIDAS right now, and this is the MIDAS structural analysis result under the conditions presented above. The first figure is the bending moment diagram, and this load combination is applied as 1.2 times of the dead load plus 1.6 times of live load. The maximum moment is 1701 kilonewton per meter at the center, and the same load combination is applied in the second figure and its shear force diagram. The maximum shear force is 876.3 kilonewton at the end, and I'll explain how I designed this gutter G1 under this condition. So if the G1 gutter is designed under the conditions suggested in the structure analysis result above, you'll get the following conditions. The size is 600 by 1000 millimeter, and the main bar is D500, and rebar with 25 millimeter diameter is used. Strap uses rebar with diameter of 10 millimeter for the ST400. I use Design Plus to design the descriptions above. For the end of G1, 6 bars HT25, 4 low bars, and HT are applied, and strap are deflected in 4 legs by designing 10 mm rebar in 150 mm interval. In the center part, 4 HD 25 top bars and 10 HD 25 low bars are applied, and strap is designed with 4 legs of D10mm rebar in 300mm intervals. Because the conditions are set to get the appropriate reinforcement plans when locating an opening in the beam, always keep in mind that the gutter size is bigger compared to the column intervals, and the load condition is not normal. Okay, so let's move on to conversion force. I've also checked the value of the point where the opening is located from the MIDAS analysis result. Moment value was 672.7 kilonewton per meter and shear force 845.8 kilonewton. So I'll briefly explain the stress caused by the external force P as M1 and V1. Next, let's take a look at the change of force. The shear force generated by external force P acts as a shear force as it is, and the moment generated by the external force P is converted into an axial force acting on the upper and lower sections. And the shear force acting on the upper and the lower sections separated by the opening is converted into moment. I'll deal with it more specifically in the following step. Number 1. Change of shear force. For convenience, the initial stress caused by the external force P will be M1 and V1. The secondary stress converted by the opening will be defined as M2 and V2. The V1 acts as shear force even in the changed section changed by the opening. Of course, since the upper and the lower parts have the same section size, the converted V2 is calculated by dividing V1 by 2. So therefore, the shear force V2, currently acting on the changed section, is 422.9 kilonewton. Next, we'll check the moment conversion that will be applied in the beam. Moment M1 by the external force P is converted into axial force, which is tensile and compression. As shown in the figure, the arm length of the force means the distance between the center of the upper section sorted by the opening and the center of the lower section. So considering the 400mm depth of the upper section, the 400mm depth of the lower section, and the 200mm height of opening, the distance of compression and tensile force is calculated as 600mm. Therefore, the converted axial force is M1. So by dividing 672.7 kilonewton per meter by 0.6 meter, we can know that the tensile and compression are changed to 1121.17 kilonewton. Of course, depending on the direction of the moment, it is converted into upper compression and lower tensile forces in this case. However, if it is at the end of the gutter, it is likely to be converted into upper tension and lower compression forces depending on the direction of the moment. Or keep in mind that the direction of tension and compression may change according to the difference in the value of the load depending on the direction of gravity and the lateral force. Lastly, shear force generates moment. I've explained that V1 generated by external force P is converted into V2 according to the size of the section, and this converted V2 generates a moment in proportion to width and length of the opening. We've calculated V2 as 422.9 kilonewton earlier, and when the width is multiplied by 0.6 meter, the moment M2 becomes 253.74 kilonewton per meter. Next, this is an example of reinforcement by the calculated force earlier. So based on the upper section, compression force is 1127.17 kilonewton. Shear force is 422.9 kilonewton, and moment is 253.74 kilonewton per meter. As you can see it here, the third figure shows the section detail of the strengthening section, and in order to focus on the force conversion, the calculation process for reinforcement is excluded. In this example, the cross tile was placed on the assumption that the upper section is the compressed section. Judging as a member with compression behavior should be considered according to each situation with the value of compression force. I'll now move on to finite element analysis. Here I've used MIDAS Gen to review the contents described above as finite element analysis. So far, we have reviewed simple calculations with equal size of sections. But if the sections are not standardized, or if the size is different, simple calculation may be difficult due to the difference in stiffness. That is why finite element analysis is attached. Since the size of the beam is 600 by 1000, and the size of the column is 600 by 600, this sample was modeled with plate with thickness of 600 millimeters. The size of the plate shell is set to 200 millimeters. And of course, if the size of the shell is smaller, more accurate values will be obtained. And if the size of the shell is larger, modeling will be easier. But the results will be approximated rather than exact values. The first figure shows the modeling shape of a finite element analysis, and the second figure shows the vertical deformed shape by external force P. So this is the analysis result. The value shown in the enlarged view is in the x direction, so it can be defined as compression force. We can access compression force based on the calculation from moment N1. In the enlarged view below, the average value per unit length of the two shell marked in blue is 5242.75 kilonewton, which corresponds with 1 meta. So calculating this value with corresponding length is 1048.55 kilonewton. It is likely to have a margin of error, which is about 6% from the previously calculated P2, that is 1121.17 kilonewton. This difference could be due to several factors, such as size of the shell. For example, the value obtained from the initial frame analysis does not set the column and the beam panel zones, and the difference in these settings may cause some values to be different from the result of the finite element analysis. Therefore, a difference of about 6% can be considered as appropriate in the calculation process for the force conversion. Since the following analysis result is FYY, that is the result in y direction, it can be assessed as the value of V2, which is the value converted by V1. The total value of the shell marked in blue is based on 1 meta, so if 2098.4 kilonewton is converted to corresponding length, it is calculated as 419.68 kilonewton. The result is very close to 422.9 kilonewton, which is the value calculated earlier. So far, we have learned about the change in the force due to the opening of the concrete beam, and although it is a simple content regarding the flow and the change of the force, I really hope that my webinar was helpful for everyone. Thank you for watching it.